Today's lesson is going to focus on enthalpies of formation. So there are four methods that we can use to determine the enthalpy of reactions. And so far we've used our ratio method, we've used calorimetry, Hess's law, and this last method is using very theoretical concept, very theoretical values, using enthalpies of formation. So enthalpies of formation are when we are talking about the heat or energy associated with the formation or synthesis, okay, another term that means the same thing, of 1 mole, this is very important, 1 mole of a compound or an element, mostly compound, from its elements in their standard states. So usually we're talking about SATP, so just remember that that's a constant set of pressure and temperature conditions that we use for gases oftentimes. So here's an example. This is an enthalpy of formation reaction right here. And there we are creating 1 mole, notice the coefficient of 1 for CO2, and we're creating that from the elements to make up CO2. There is an enthalpy of formation, right? Or enthalpy associated with the formation or synthesis of this compound. So we'll put a little F beside delta H to imply that. And we'll use enthalpies of formation as just another method in which to calculate the overall enthalpy of a particular reaction. So the first thing we want to do is get comfortable with a formation reaction. Okay, so these are the same as synthesis, okay? Keep that in mind. Formation is just a different term we're using. It's the same as synthesis. So this is where we're going to create or write out reactions where we're creating 1 mole of a compound from its elements. We usually include the states, and let's practice with 2 of them. So if I wanted to write out the formation or synthesis for Fe2O3, I would do this using its elements. So I would need some iron, which is in a solid state, right? It's a metal. I would react that with some oxygen, which is in the gas state, and I would form this compound. So this is rust, Fe2O3, and this would be solid, right? So synthesis of ionics. Ionics are always solid at room temperature. Now, the thing is, we don't know we have to balance reactions, but remember, I have to have 1 mole. So I cannot put a coefficient here at all. It has to be a 1. So in order to maintain that, I'm going to have to put coefficients in front of my other substances. So I have to balance that iron, and I put a 2 in front. But I have to balance my oxygens, and this gets kind of, a little complicated because I have the odd even thing happening. But in order to get 3 moles of oxygen over here, I can use a fraction of 1.5, and 1.5 times 2 gives me 3. So sometimes we do use fractions. We don't like them in chemistry, but every once in a while we will, in order to maintain, as we do here, 1 mole of Fe2O3. Here is butane. So let's write out the reaction to make 1 mole of butane. So we would take some carbon in the solid state. We would take some hydrogen. Remember, hydrogen is diatomic, just like oxygen, so in the gas phase. And then we would create our butane, so C4H10, which is a gas at room temperature. This one's a bit easier to balance. So again, you have to maintain a coefficient of 1 right here. So that means we need a 5 in front of hydrogen, and we need a 4 in front of carbon. So these are the types of formation reactions that we're using. And then there'll be enthalpies, associated with each of these. And it is these enthalpy values that we use in this particular method. So in your data booklet, you will have a chart of enthalpies of formation. You won't have the formation reactions, but you'll have all these compounds listed there. And again, we understand how we obtain these enthalpy values. It's by synthesizing these compounds. So for example, if you go to your data booklet and look up magnesium oxide, you should see an enthalpy of formation value listed there. of negative 601.6 kilojoules per mole. Note that any element on the periodic table in its standard state, okay, that means that, you know, if on the periodic table oxygen is a gas, which it is, it's already created, it's already synthesized, it's already formed, its enthalpy of formation is 0. It exists already. You don't have to make it. Iron in the solid state, again, it exists naturally. Enthalpy of formation would be 0. But if I needed to melt iron and put iron in the liquid state, now there will be some sort of enthalpy of formation value. It won't be 0 because we had to melt the naturally occurring iron solid, and then there would be a formation value for it. But anything in its standard state has already been formed and its enthalpy is 0. So what we do is we take these enthalpy of formation values and we use them in an overall chemical reaction. And so the enthalpy of your entire reaction will be based on the enthalpies of formation of those products, and we subtract off the enthalpies of formation of the reactants. If there are any coefficients or mole terms in front of your reactants or products, you multiply those by the enthalpy of formation value. And then for all of those products, we would take the sum of it, right? That's what that symbol means. And the same thing, sum of all of the reactants. And then we subtract off reactants from products. So here's an example where we would use enthalpies of formation. And we know that we need to use it here because read this question. It says, what's the molar enthalpy of combustion of propane? And they don't give us any values at all, no data. So, you know, no change in temperature. So we know we're not using calorimetry. No sub-reactions. So we know we're not using Hess's law. No enthalpy of the original reaction. And then we're changing an amount like we would in ratio method. So this is very theoretical, and we're using these values that we find in the chart in our data book. But you have to have a reaction written out. So this is an example of you knowing the formula for propane and then writing out a complete combustion reaction. So I'm going to give you a minute and stop the video, do that yourself, balance it, and then come back and check what I've done. So make sure that you have the states written of all of your reactants and products. With the combustion reactions, water is always in the liquid state. This is very, very, very important that you know that. And then what happens is combustion reactions are so exothermic that the water evaporates right away. But when we go and balance this, we would have 4 moles of water, 3 moles of CO2, 5 moles of oxygen, and then my propane stays at a coefficient of 1. So let's start to set up this solution. And there's our formula or our calculation formula for an enthalpy of formation. So we want to know what is the overall enthalpy for this particular reaction. We have to deal with products first. So we come over to our reaction and we notice that there is a molar coefficient in front of CO2. So we're going to say we have 3 moles of CO2, and we're going to multiply that by the enthalpy of formation of CO2. So you have to go to your data booklet to look this up. And when you do, you'll see that CO2's value is negative 393.5 kilojoule per mole. And again, we don't have 1 mole, we have 3. So these mole units will cancel out. And then we have another product. So this is where this fancy symbol comes in. This is the summation, right? So we have to add on now for water. So we have 4 moles of water, and we need the enthalpy of formation for water in the liquid state. Be very careful because the gas state is there as well. And keep track of all of these negative and positive signs because it's important. You're going to be adding these up at the end, and it's easy to make a mistake. So that's it for my products. And then we're going to be subtracting off the enthalpy of formation of my reactants. So for propane, I have 1 mole of propane, and I multiply that by the molar enthalpy of formation for propane. So off you go to your chart, and you notice it's negative 103.8. And again, that is kilojoules per mole. So again, all these mole units are going to cancel out, which is a nice thing. And then I'm adding on my other reactant. So I have 5 moles of oxygen. And you can go and look up the molar enthalpy of formation for oxygen, but you will not find it because it is an element and it's in its natural state. So its enthalpy of formation is 0 kilojoules per mole. Okay, so now the math is easy, but just keep track of all your negatives and your positives. And it's a good idea to write out all of the values. Okay, do this in baby steps so that you don't make any mistakes. So we're going to end up with negative 1180.5 kilojoules for CO2. We're going to add on water, which works out to be negative 1143.2 kilojoules. And then we are going to, we'll put that in square brackets, subtract off propane's enthalpy of formation, which is negative 103.8 kilojoules. When you do all of your math, you should be getting negative 2219.9 kilojoules. Here's another example. It's the same, but a little different. 1 mole of a metal oxide reacts with carbon monoxide as shown below. And it says that the enthalpy change is negative 24.8. So this is telling us that the enthalpy change for the entire reaction is equal to negative 24.8 kilojoules per mole. So it says, what is the standard enthalpy of formation of the metal oxide? So we're trying to figure out what is the delta HF of this oxide. So I'll set up the equation for you. So we know that the enthalpy of the reaction is negative 24.5 kilojoules per mole. And then we're going to start subbing in our values for products and reactants. So for my products, we have 3 moles of CO2. So 3 moles, and again, enthalpy of formation for CO2 is negative 393.5 kilojoule per mole. And then we're going to be adding on 2 moles of this unknown element X. Well, it doesn't really matter what X is. X is going to be a metal of some sort. We already know this. And it's in its standard state, so we know it's going to be 0. So we really don't care about the identity of it at all. We're going to subtract off the product or the reactants. Now, here we go. This is the one that we don't know what the enthalpy of formation is. We know that there's only 1 mole of it, and so we're going to leave it as a delta HF value. And this is what you're going to be solving for. That's your unknown. We're going to add on 3 moles of carbon monoxide. So 3 moles, and carbon monoxide's delta HF is negative 110.5 kilojoules per mole. So take a second here and rearrange this. This is your unknown. This is what you're trying to solve for. And hopefully you get to the answer that you saw on the previous slide.